Hi everyone, this is going to be a video walkthrough going over problem 2, which is MSD Radix Sort. So quick agenda, I'll first be giving a brief overview of MSD Radix Sort, then I'll be diving through the problem and live coding the solution. Okay, so let's start off with a quick review of MSD Radix Sort and Radix sorts in general. So the main question Radix sorts are helping us answer is, what if the items we are sorting are composed of digits, right? In that case, what if it's potentially faster to sort these items digit by digit, okay? So for a quick example, let's look at MSD Radix sort on the following numbers right here, okay? So I said before, we're going to sort these numbers digit by digit. And what MSD means is we're going to sort them from the most significant digit to the least significant digit. Okay. So what is the most significant digit in a number? It's the leftmost digit. And if we're sorting strings, it would be like the leftmost character. Okay. So when we're sorting all of these numbers, we're going to start off by looking at that most significant digit, which amounts to looking at this column, right? So what we're going to do is sort all of these numbers on the most significant digit, right? And now you may wonder, if we're sorting all of these numbers on the most significant digit, why don't we just sort all these numbers period and just be done? Well, it turns out that if we're sorting all of these numbers on a single digit, and we know that this single digit is in some range, in this case, the range for any digit is between 0 and 9, it's actually pretty fast to sort all of these numbers using something called counting sort. Okay, so when all the items we're trying to sort are within a certain range, right? Since we're trying to sort these numbers on this digit, and a digit is always between 0 and 9, counting sort is a pretty efficient way of achieving that. But I won't be getting into counting sort for this walkthrough, but just important to keep in mind. Okay, so back to this problem, or back to the situation at hand, we're trying to sort all of these numbers. And what we've done so far is we've sorted them on this first digit, okay? What this results in is now we have partitions, okay? We can kind of think about each of these partitions as groups that are equal in the digit we are comparing, right? If we think about this partition right here, it contains all of the numbers whose first digit is 1. This partition contains all of the numbers whose first digit is 4, right? These two partitions contain all of the numbers whose first digits are 7 and 9 respectively. And if you can hear sawing in the background, I apologize by that. There's some yard work going outside. Okay, but back to this problem. So when we run MSD Radix sort, we first sort them into these groups. And if it turns out that a group has 0 or 1 numbers, all that we need to do is just put that in the final answer, right? So in this case, since we take these two groups and we see, oh, there's only 1 number in these groups, we don't have to really sort these partitions, right? But if it's the case that we have a partition that has 2 or more items, we need to recursively sort this partition. How we're going to do that is, the next time I call MSD Radix sort, let's look at this top partition for an example. We're going to be looking at the next digit in the number, right? And then in this case, since both of these are equal, we are left with another partition of size 2, and then we finally look at the last digit, and then we are able to break it up into 2 numbers, okay? So the takeaway here is that when we're running MSD Radix sort, what we're doing is we start off by comparing all of the numbers by the most significant, i.e. leftmost digit. Then what we do is we slowly make our way to the right until we hit the least significant digit, right? So that's the main idea behind MSD Radix sort. And one other takeaway here before we dive into the actual problem is that when we're trying to sort all of these numbers, in lecture we use counting sort, but it doesn't really matter what sorting algorithm we use, right? Counting sort is good because it's pretty efficient when all of the things we're trying to sort are within a certain range. But it's possible for us to use any sorting algorithm so long as that sorting algorithm is sorting based on this digit. So in the problem that we're trying to do right now, instead of using counting sort as the subroutine, what is a subroutine? It's just like the function that we're using to help us solve the bigger problem. We're going to be using the stable sort method, okay? And the only reason for that is that the stable sort method turns out to be one line of code because it calls an inbuilt Java sorting method. So just out of convenience. All right, finally, it says that we can use the stable sort method, and it says we can also use these methods of the list class. Okay, so these two methods will become more apparent as we dive into the problem. So I recommend, if I was a student doing this problem, the first thing I would do is kind of look at the skeleton code provided, right? Try to make some sense of what's happening here. Okay, so what's really happening here is that we're trying to implement this public static list MSD function, right? And since MSD is a recursive algorithm, it's provided to us this larger overloaded MST function, right? So the hint is that we're trying to implement MSD recursively, but we need some sort of index that's going to be passed during these recursive calls, okay? That's why we need to use this helper function. So without further ado, let's actually live code the solution. I think it's a little more fun than using the discussion. So I will transition to my laptop now. Okay, so all I did was take the code from the discussion worksheet and just kind of put it in IntelliJ, and then I created a quick example. So the first thing I kind of want to do is let's fill in this method here, and let's start filling in the MST method until we realize an example would be a bit better, okay? So let's try to put down everything we know first. So in the MST function, we should probably issue a function call to our helper function. So we will do MSD on items, because what else are we going to call it on? And then we should also try to figure out how we're utilizing this index, right? So recall in MSD Radix Sort, through that example we walked through, we can kind of imagine that the index is going to be where we are in the current string, right? So suppose the string is hello, right? What we'll realize if the string was hello is that the index should start right here, because we're first going to be comparing letter H. Then the next time we recursively call our function, the index should move to E, right? And then it should keep moving to the right until we get to the end of that word, okay? So with that in mind, when we're indexing into strings, we should probably do index 0 initially, because that's going to be letter H, okay? All right, so we figured out what to put here. Now we should figure out the base case for our function. So I think there's two base cases here. And the first base case I think is a bit easier, and it's the one we saw in our example, where if the list of items only has 0 or 1 elements, it means we're done, right? Again, I apologize for the sawing in the background. So if items.size is less than or equal to 1, it means that items is already sorted, right? So there's no work that we really need to do. So another base case, actually, which is not as immediate to think of, is trying to solve the situation where we have two of the same string, right? Suppose I have two of the same string. What's going to happen is that these two strings are just going to keep ending up in the same partition, right? So eventually index is going to point to one letter past the end of these strings, in which case we should just put these two equal strings and return them, right? So if everybody in items is equal, we should just return items, right? Well, how do we know everyone in items is equal? Well, it means that we looked at all of the indices in these two strings, and we couldn't put the two strings in different partitions. So if index is greater than or equal to items dot get 0 dot length, okay, this is exactly the same thing I'm saying, it's just a bit more confusing, I think. So what this is saying is that if the index I am at, right, recall in my drawing that this is our index. If it's past the size of the string, right, it's somewhere over here, that's what this is saying. Well, why can I access the first string? Because we know all of the strings are the same length, right? Since all of the strings are the same length, I can just simply check if index is greater than or equal to items.getZero.length, right? If it's past the length of one string, it means that this partition contains all of the same string, right? So our base case, once more, if our partition contains all of the same string, or our partition is of size less than or equal to 1, we know it's already sorted, right? Okay, so moving on to this section. So when we kind of look at what's provided to us, when we run MSD Radix Sort, what we're doing is we have our initial list of items. Okay, then what we want to do is sort these items on a given index, right? That's the first step. The second step is to break up our sorted list of items into partitions and recurse on each partition. So breaking it up into those two steps, we see the first step is to call our stable sort on our, I'm going to call this items. It's a little inconsistent with the worksheet. Okay, so we want to call stable sort on items on the given index, right? So what this is going to do is sort items. So now, if I call stable sort on this example, what's going to happen is this list of strings is going to be sorted. So we'll put apple first, then probably heave. Oh, just kidding. I know my alphabet. Then eagle, enter, heave, hello, human, and sport, right? So all we've done here is we've sorted all of these strings on their first letter, right? Ooh, actually, I made another slight mistake. So since we're only sorting them on the first letter, we're not sorting them on the second letter. So that means that enter should come before eagle, right? Because that's the ordering that P is here. And then when we look at heave, hello, and human, we know it should go in the ordering of hello, heave, and human. Okay. So my apologies there, small mistake. But yeah, so all we've done is we've taken this list of strings and we've sorted them based on their first character, and we've done so in a stable fashion, right? Okay, so the next step here is we want to break up all of these strings into their own partition, right? So this should be one partition, this should be another partition, this should be the third partition, this should be the fourth, and we should recurse on each partition. So in order to recurse on a given partition, we should use the sublist function, right? What sublist does is it takes in a given list and it returns a sublist, which is like a smaller sublist from that given list, okay? So my idea is let's iterate through all of the indices in items, right? That's what this is doing. And we're going to have start be the start of our sublist. We're going to have end be the end of our sublist. And then we're going to keep creating partitions, recursing on the partition, and then changing start and end. Okay? So for a quick example, let's say that I start is at 0, end is at 1, right? So in this drawing, what that kind of looks like is we have start at 0, and we have end at 1. And when we call our sublist function, let me just kind of put that down. So if I do list.string, sublist is equal to items.sublist, notice that sublist takes in a from index and a to index. We can kind of look at the signature here, where the from index is inclusive, right? And the to index is exclusive, right? So over here, if I put start and end in their current state, since end is one after the actual end of the partition, it works because end is exclusive. So in this case, this sublist, if I call it on the given start and end, as shown in the drawing, we will get the single partition containing apple. Well, the next question that arises is, how did we know that we needed to create a sublist here? Like, why couldn't we move end a little farther before creating the sublist? Well, the reason is that when we compare apple's first letter to enter's first letter, we see it's different, right? So the idea behind that is we want to say if items dot get of start, right? Because start is one word, and then we're going to look at the character at the index is not equal to, sorry about this. Let me see if I can zoom out a bit. Okay, there we go. So what it's saying here is that if the items.getStart.char at index is not equal to items.get end, because we want to be comparing the string at start to the string at end, if they're not equal, it means we found the end of one partition. In that case, what we want to do is create a sublist containing that partition. We want to recurse on that partition and take all of those sorted words in that partition and add them to our final answer. So we'll do answer.addAll, the recursive call on our sublist. And then when we recurse on a partition, we want to increment the index by 1 because we're going to be comparing the next index in the string in that recursive call. So here, oh, my laptop's a little laggy. I apologize for that. Okay, so here we're going to put index plus 1 because when we recurse, we want to look at the next index, right? Of course, looking at one example, when I recurse on the partition with enter and eagle, we want to be comparing n and a, right? So that eagle and enter swap. Okay, then what we want to do is that we've successfully taken the partition apple. We've passed it into a recursive call. So we want to move start where end is currently, right? That's the idea here. Now we want start here, and we can also just like leave end here because we know that end will move at the next iteration. Okay, so the idea here is that we want to say start is equal to end because we're looking at the next partition. Okay, so this is almost the final solution. We're just missing one quick edge case. And what that edge case is when end eventually gets to the end of items, at some point it's going to have to go one past the last index, right? So in that case, what's going to happen here is that we want to have an if check where we say that. So if end is equal to items.size, what this is saying is that since this for loop goes all the way till less than or equal to items.size, we know at the very end will be equal to items.size. In that case, we know the partition is over because like there's no other elements to include in that partition, right? So what we want to do is create that partition as usual, right? And the example that kind of promoting this instance is we know at the very end, what's going to happen is that start will be at sport, and then end will go one past. In that case, we still want to recurse on sport. So what we do is we just simply issue a recursive call to MSD, where the sublist goes from start, which is pointing to sport, to end, which is one past the end of the list. So this is all for the video walkthrough. I hope you all found it helpful. I'll quickly clear these drawings and we can kind of zoom in on the solution a bit more. So yeah, that's all. Have a good rest of the day.